Hey there people, Jay here. So in this video, first we'll briefly discuss about the assumptions that are related with conducting students t-test as well as t-test with Wells correction and the non-parametric manual t-test. So for conductance of students t-test, both the groups should follow normality if the homogeneity of variance is not met, but we have equal study design. That means both the groups have equal number of observation. We can still go with students t-test if the homogeneity of variance is met, but if we have unequal study design, then still we can perform students t-test. On the other hand, again, if the normality is met, but homogeneity of variance is unequal, also the study design is unequal, then we better conduct t-test with Wells correction. And if the normality is not met in the first place, then we can go with non-parametric test, that is Mann-Whitney. A paper published in 1981 by Conover and colleagues suggests that even if the normality is failed, but based on the homogeneity, we can perform the t-test or the t-test with Wells correction not on the raw data, but after transforming them into ranked values. Now, let's talk about p-value, power, and effect size. A statistical hypothesis serves as the researcher's educated speculation regarding the anticipated outcome of an experiment. It represents, in a verifiable manner, the proposition that the researcher intends to investigate within a sample in order to determine the accuracy within the relevant population. In statistics, there are two types of hypotheses that are commonly employed: the null hypothesis or the alternative hypothesis. The alternative hypothesis essentially represents the researcher's forecast of the expected condition of the experimental group following the implementation of the experimental treatment or any other intervention. On the other hand, null hypothesis posits that there will be no impact resulting from the experimental treatment. Before conducting a study, the researcher must not only state the hypothesis but also determine the alpha level at which the hypothesis will be considered supported. In simple terms, the alpha represents the probability of erroneously rejecting the null hypothesis when it is actually true. The most commonly chosen significance level, denoted as alpha, is typically set at 0.05. This means that the researcher is willing to accept a 5% chance that a result supporting the hypothesis will be false in the entire population. Another important statistical measure is known as the p-value. The p-value represents the probability of incorrectly accepting the alternative hypothesis. It is compared to the alpha level to determine if the result is statistically significant, indicating that the observed result in the sample is likely to hold true in the entire population. If the p-value is equal to or greater than the alpha level, then the alternative hypothesis is accepted. Conversely, if the p-value is higher than the alpha level, the alternative hypothesis is rejected and null hypothesis is accepted. There are two distinct categories of errors that can occur in a statistical analysis. The first type of error, known as a type 1 error, involves accepting an alternative hypothesis is true when it is actually false in the population. This is often referred to as false positive. Sorry. The probability of committing a type 1 error is defined by the alpha level. Type 1 error can arise due to various factors, such as inadequate sampling, leading to experimental sample that significantly differs from the population, or errors in the design and implementation of study procedure. On the other hand, a type 2 error occurs when the null hypothesis is incorrectly rejected, resulting in the acceptance of alternative hypothesis when it is actually false. This is known as false negative. The probability of committing a type 2 error is denoted by the beta level. Small sample sizes, particularly when combined with low or moderately low effect size, are the most common causes of type 2 error. Both small sample sizes and low effect sizes diminish the statistical power of a study. Power, which represents the likelihood of correctly rejecting a null, sorry, uh, the power represents the likelihood of correctly rejecting a false null hypothesis, can be calculated as 1 minus beta. Alternatively, it can also be expressed as type 2 error probability. For instance, if the probability of a type 2 error is 0.15, the power of the study would be 0.85. It is important to note that reducing the probability of committing a type 2 error increases the risk of committing a type 1 error, and vice versa. Therefore, it is crucial to establish a delicate balance between the minimum acceptable levels for type 1 and type 2 errors. The ideal power for a study is typically considered to be 0.8, which can also be expressed as 80%. The adequate sample sizes should be maintained to ensure a type 1 error as low as 0.05 or zero point 0.01 and a power as high as 0.8 or zero point 0.9. Nevertheless, it is important to note that power value below zero point 0.8 does not automatically render a study completely worthless. In recent years, the concept of cost-effective sample size has gained significance. Moreover, the commonly chosen alpha and beta error limits are typically arbitrary and are used as convention rather than being grounded in scientific validity. While increasing the sample size is recommended to reduce type 2 errors, it comes at the expense of higher project costs and potential delay in the research completion within the anticipated time frame. Effect size. The effect size is crucial measure that provides valuable information regarding the predictive ability of the independent variables on the dependent variable. A low effect size indicates that the independent variable have a weak predictive power as they are only minimally associated with the dependent variable. On the other hand, a strong effect size suggests that independent variables are highly effective predictors of the dependent variable. Therefore, the effect size plays a significant role in assessing the clinician's ability to accurately predict outcomes based on the independent variable. To comprehensively evaluate the impact of a study and determine its clinical significance, it is essential to assess the effect size in conjunction with the statistical significance. While the p-value is important for statistical evaluation, as it indicates the presence or absence of an effect, it does not account for the magnitude of the effect. For a comprehensive presentation and interpretation of a research finding, both the effect size and statistical significance, that is p-value, should be provided and taken into consideration. The discussion on the appropriate sample size for the student's t-test begins by emphasizing the distinction between producing sufficiently powered results and producing robust results. While robust results indicate relative accuracy even in the presence of violations of the assumptions, they do not necessarily guarantee a sufficiently powered test, which is the ability to detect a statistically significant difference if it exists. Conversely, it is possible to have robust results for an underpowered test, where assumptions are met, but the sample size is insufficient for detecting a difference. Additionally, a sufficiently powered test may not necessarily produce robust results, as the sample size may be adequate for detecting a difference, but assumptions have been violated. So now we'll look at the Cohen's delta for measuring the effect size of independent sample t-test in SPSS. So the effect size D, the concept was given by Cohen in, I guess, 1982 or something like that. Please correct me if I'm wrong. It is measured in standard deviation units. If the sample size is more than 50, then Cohen's D should be reported. Cohen's D of zero point 0.2 represents a small effect size. Cohen's D of zero point 0.5 represents a medium effect size, while zero point 0.8 represents a large effect size. If the number of observation is less than 50, then instead of reporting Cohen's delta, we can report Hedges G, which takes into the account the limitation of small samples and provides better results. And of course, this is only valid if the homogeneity of variance is met. But if the homogeneity of variance is unequal, then instead of reporting Cohen's delta or Hedges G, we can report Glasses D value. So here I have given an example. I have conducted a t-test in SPSS. As you can see, we have two groups here, both having 20 observations. Both the groups have equal number of observation in them. The mean of group 1 is 24 and for group 2 it is 38. So we conducted a students t-test to statistically check if the significant difference exists. So after checking the homogeneity of variance, which was not significant, the t-test revealed a significant difference between the mean values of two groups. Then we check for the effect sizes. In SPSS, while conducting the independent sample t-test, the effect size are automatically calculated. As we saw in the previous slides, we have equal number of observations, but the observation number is less than 50. So we will report Hedges corrected Cohen's D value, which is 6.613, which signifies higher effect size. But for example, if the homogeneity of variance is violated, then we would go with Glasses delta to report the effect size, which in this case is 2.05, still a higher effect. So thank you guys for watching this, and if you have any suggestions or questions, please comment down below and we can discuss in the future videos.